The last C-level control flow form we'll look at is a switch statement. So here we're switching on X, and we have cases for 1, 2, and 3. And so what this means is that if X's value is 1, then the control should jump here. And then break within that case means once you've done this assignment to W, then break out of the switch. That is, jump down and return to W. If X is equal to 2, then we jump here, and so on. But notice that case 2 doesn't have a break after it. So if X is equal to 2, we'll do this, and then we'll also do this before breaking out of the loop. And that's called a fall through. Usually not a good idea, but sometimes it's an okay way to go. Right? If X is equal to 5 or 6, see 5 falls through to 6, this is the more common and useful way to fall through. It's really just merging some cases together. Then control jumps there. If X is any other value, if it's less than 1, or if it's 4, notice we didn't have a case for 4, or if X is greater than 6, in all of those cases, then we jump down to here. The default label means case everything else. There's no break, and break's not needed because it just falls through and returns. So how do we implement this kind of switch statement? One possibility is to use ifs to figure out what numbers are relevant and then jump to suitable labels. And then where we have breaks, then we jump to a done label that follows the switch. So if we had 1, 2, or 3, then we might get a pattern like this, where we check whether X is 1, 2, or 3, and if it's not any of those, then we go to default, or since there's no default here, we just jump to the done place. That is what a compiler is likely to do if the number of cases are small, or especially if the number of cases are small relative to the range of X here. On the other hand, if you have many cases and they're dense, so suppose we're going from 1 to 99, you could imagine doing a binary search or something like that, but what the compiler might do instead is use a jump table. So a jump table idea is we have these labels here, and you can imagine lining up those labels in an array and then just selecting the right label out of an array. This bit of code is not standard C code, but it is GCC code. When you use a double ampersand in front of a label name in GCC, that means give me the label as a value. And so jump table is going to be is an array of label values. And then we can look at X. As long as it's between 1 and 99, then I subtract 1 off of X because I want this first slot in the array, which is index 0, to correspond to X equals 1. Pull out the corresponding label and then go to star. What that means is this expression produces a label, and you should go to that label. If X is anything other than within the range 1 to 99, then I can go to the done label. To get a sense of how the assembly instructions work, let's see what happens if you take this C code and run it through GCC. I have over here jump, which has that jump function. We're setting up a jump table with labels 1, 2, and 3. I don't have the -1 here. Let's put that back in. Well, let's make it like the slides. No -1. Okay. So 0 is going to the 1 label, 2 is going to the 1 is going to the 2 label, and so on. And I've got a main which is calling jump with 1, -1, -2, -3. So since 1 corresponds to this bit, it's going to return a -2, right? B is what happens in the 2 label. Let's take this code. I'm going to compile it with GCC to a J program. Use a little optimization, compiling jump with main. When we run it, we got the -1 as expected. No, I expected -2. That's because I modified the file. Let's try that again. The -2 as expected. Let's look at the machine code that we got here. So if we dump all of the code, there's main, here's jump. Jump is what we care about. There's a lot going on here. Let's go back to the slide view of it. You can see that this view is, you're going to see something like this on the slide. What you see is I'm moving this address 4005552, which corresponds to here, that move expression. Right, that's getting moved in some places relative to RSP, and then we're doing a calculation there. But let's look on the slide version. The key jump, the dispatch, is right here. but the dispatch has this elaborate expression over here that needs some explanation. V is going to be in the RDI register. Sorry, EDI register, or RDI, but it's EDI because it's an integer. To do the jump table calculation, this pointer calculation that's behind this array lookup, we need a 8-byte value though. So that's why the code right here takes V and sign extends it to an 8-byte number. And then it takes that number and multiplies it by 8. Why does it do that? Because each of these labels takes up 8 bytes. So we're using V as an index into this table. That means we multiply that index by 8, add it to RSP, and the reason is that table has been set up relative to RSP here. And in particular, it's relative to RSP starting at negative hex 20. So here's where that table is set up, starting at negative hex 20 relative to RSP. We put, corresponds to the label 1, the label 2, the label 3, and you see these same numbers down here. That's label 1, label 2, label 3. Much like the other code we saw, there's no actual jump to done here. There's no go to done. Instead, it just returns V right away after moving various values, A, B, or C, in place of V. You also see this no op here. The reason the compiler put that in is just to make some things line up nicely.